What's a coefficient? Yes, ma'am.
Then a coefficient is the number in front of a variable.
Yes, so a coefficient in front of a radical would be, for example, 3 root of x. Or we sometimes say 3 square root of x. Or we sometimes say 3 radical x. Those all mean the exact same thing. That's called a mixed radical because it's got both pieces. Another example could be negative 4 root x. There's another mixed radical. Mm-hmm. Another could be negative radical 20. Whoa, hold up now. Whoa, what's the coefficient there? There's no number in front. What is going on? Yeah, so we know there's a little imaginary negative 1 in there that we don't see, but we know it's there. Those are all called mixed radicals because it has the two pieces. What do you think an entire radical is? Just a radical, so no coefficient. Just a radical. And what that means is the coefficient is really just 1. So an example could be root of 21. Example could be cube root of x. Another example could be the root of xy squared. Those are all called entire radicals. So first thing we're going to do, and then the opposite, is we're just going to convert from one to the other. Again, just like you learn with fractions, converting improper to mixed, mixed to improper, we're just doing the same thing with radicals. So we're going to change negative 3 cube root of 2 to an entire radical. Why? That will come when we do the adding, subtracting, multiplying, dividing. So we're just doing the skills now to be able to use them next week. Do you want to see an example first and then the method, or do you want the method first and then the example? Method first. Move the coefficient under the radical sign. Move the coefficient under the radical sign. Give it the exponent. Equal to the index. That's why we practice the vocabulary, so you would know what an index was. And again, if you're not a wordy person, this probably means nothing. Don't panic when I do the example. You'll see what I mean. So move the coefficient under the radical sign. Give it the exponent equal to the index. Step number 2, simplify. This example I'm going to do right beside, just so you can see it right beside the method. So I'm going to write it over here. So we have negative 3, and then the cube root of 2. Step number 1, I'm going to grab that negative 3, and I'm literally going to just shove him under the radical sign. So I'm going to keep the radical. I'm going to keep the index. I'm going to keep the 2 that was already there. And all I'm going to do is shove negative 3 behind him. Why did I bracket the negative 3? So mathematically, why are those brackets important? It's a multiplication, and if I didn't have the brackets, what would I be doing? A subtraction. So you may want to add the instructions that if it's negative, you have to bracket. If your brain needs those, feel free to add that in. The second part of this step, I'm going to grab my red pen just to show that it's important. Not that everything in math isn't important. And all I'm going to do is copy whatever the index is I'm going to give them an exponent. So let's talk about y. Again, you don't need to know the y, you only need to know the how, but I like to show the y because some brains need it. So tell me, what is root of 16? I just heard 4 answers all at the same time. Let's try it again. What is the root of 16? 4. So if I wanted to take that 4 and turn it back into a radical, what I would do is I would stick it under the root sign, and what would I do to the 4? Square it, because the opposite of square rooting is squaring something. So when you put it back under, you have to do the opposite. Well, what's the opposite of cube rooting something? Cubing something. That's why you're doing it. Why is the paper like mysteriously pink and now it is not? Did you see that too?
No.
That was so extremely weird. Okay, that's why. You're just doing the opposite of what's done to be able to put it back under. Step number 2 is simplify. This comes down to bed mass. I didn't mean to do this in black. It really bothers my left brain now that it's not purple, but I'll deal. The next step is bed mass. So what comes first, multiplication or exponent? Exponent comes first, so I'm going to leave the 2. I'm just going to evaluate -3 times -3 times -3, which is still bracketing at this point because I still want to keep my multiplication. And the last step is just to multiply together, so 2 times -27, -54. If we were to put into our calculator -3 times the cube root of 2, and we would put into our calculator the cube root of -54, what would we find?
Wait, so the cube root of what? And then
We're not going to, but let's just pretend we were actually going to put these into our calculator. What would we find if we put these both in?
the same answer.
They're exactly the same number. This is just like you can have 1.5 and 3 on 2. Is 1.5 any different numerically from 3 on 2? No, this is the exact same thing. They just look different. We just need 2 different forms to be able to do what we're going to do next week. Erin. Thank you. Now we're good?
Yep.
No, we want the red off. Red means mute. So we want no red.
Okay.
Okay? So these are not any different number. They just look really different. And that's all we're doing is practicing going one to the other. Why? I'll show you next week when we get to the adding and subtracting. Let's do another one. Oh my gosh, just putting variables into it. Yes, yes I am. Who are my right brains? My lovely right brains, you have such wonderful qualities. The thing you do not have, most of you, is attention to really fine detail. And what's going to happen with this is you're going to look at this and not know if that 4 is an exponent on the a or if it's the index of the root. And so right brains need to pay really close attention to these questions. How do you know if that 4 is part of the root or it's part of the a? Well, if it's the index of the root, that little straight line will come under it. If it's not, then it's part of the A. And again, to a right brain, they probably look like the same thing because you're not detail people. Lefties were detail people. So you may want to make a note that if it wants the 4 to be the index, that little hook on the root will go underneath it. Did Jared tell you last semester why square root looks like that? Okay, so just a little bit of history here. Where does that come from? Well, way back when, they called it a radical in Egypt, which went to Greece, which went to Latin, which went to English. So the original is not radical, but it was very similar. And they used to say R2. And then as time went by, they made the R a little bit bigger. And then as time went by, the R became a little bit bigger. And now we have a square root. So it just means R for radical. Okay, for the right-brained people, what you might want to do when you look at this question is actually just split the coefficient piece from the radical piece, because that might help your brain see a little bit better what's an exponent, what's an index. That's not part of the index. That's 2a to the 4 times root of a. Process doesn't change just because they're variables. You're still going to take whatever that coefficient is, you're going to shove it under the root and give it an exponent. So I'm keeping my radical sign. I'm keeping the a that was already there, not touching him. I'm grabbing all of that coefficient. And I just need to give it the same exponent as the index. We don't see an index, but what do we know it is? 2. Tasha.
For some reason, I still can't tell whether or not the little thingy is actually under the
Okay,
4.
so let me draw it really big what it would look like if this was a 4th root. It would look like 2a, the 4th root of a. Do you see the difference in those? Yeah, and again, right brains, these tend to look very similar to you guys. So you just want to make sure you're really taking a look of, is that an index or an exponent?
Yeah, I am right brain, that makes sense.
Taylor. Why is the exponent 2? So we don't see it in here, but this is called a square root. And the opposite of squaring something, or square rooting, is squaring something. What do we what? No, Because anything to the 0 is? 1. Anything to the 0 is 1, exponent law from last semester. Okay. Step number 2 is to simplify. So bed math. Oh, hello. Hello.
Sorry for interrupting. Could you please have Marjorie's clothing to the office, please?
With her stuff, without her stuff?
No, not without her stuff. She should be back shortly.
What did you do?
Okay.
Okay. What did you do? If you come back crying, then we'll know something bad. Okay, now we just need to do the simplifying piece, and really this is no different whether it has a root or not. So if your brain doesn't like the root, then just pretend it's not there, and this is like a grade 9 exponent law question. What do we do when we have an exponent and a whole bunch of crap in brackets? We give the exponent to everything, right? That's exponent law number 3. So I'm going to keep my root, I'm going to keep my a for now. Now this step you don't need to show, but I'm just going to show for the left brains. We're going to do 2 to the 2. And we're going to do 2 to the 4, a to the 4 to the 2. Okay? That's an optional step. That's just showing you we're applying the exponent to everything. And so I'm not worrying about that a out front yet. I'll worry about him in a second. 2 to the 2. A to the 4 to the 2. A to the 8. Okay, so I'm just going to bracket this step. This is optional. You don't need to show that work. You can jump straight from the first to the second. And the last thing I'm just going to do is clean this up. We want the coefficient first, so I've got a 4. And then if I have an a to the 1 and an a to the 8, and I'm combining them, how many a's do we have? A to the 9.
Well, this is really crazy, man.
It is crazy when it's the first time you've seen it. It is.
To keep up, to be honest.
Ask me to slow down if I'm going too fast, or you can always watch me tonight or all weekend. You could watch me all weekend, 24/7. You could just put me on continuous loop and watch me. She's like, no, not going to happen. Again, to you, I understand these look very different. To a mathematician, these are the exact same thing. They just are different forms. Again, it's just like 15 on 4 would be the same as 3 1/4, right? Same idea to us. For which values of the variable is this radical defined? This question will be the bane of your existence. This is going to come up in almost every homework question. And what they're trying to do is get you to decide over the course of the unit is when can you take a square root and when can you not? What kind of numbers can you square root and what kind of numbers can you not? What about cube roots? What about fourth roots? So what kind of numbers can you not take the square root of? Can't take the square root of 0. Well, you can because 0 times 0 is 0. What kind of numbers can you not square root? Negative numbers. So negative 9. What number times itself equals negative 9? Nothing. So what they're trying to get you to understand, and this is going to come up over and over, is that the radicands have to be positive when you're doing a square root. Whatever we stick in there for a has to end up being a positive value. Otherwise, it's impossible to do the question. So when it asks you this question, for which values of the variable, it's asking you what are the values of a that are going to make this expression greater than 0. I should say, or equal to. And greater than or equal to is just a fancy word of saying positive. So if you're a wordy person, what we're doing is taking the radicand, and we're about to solve it for 0. Well, this is just an equation, just like any equation. We do the opposite to get rid of stuff. What's the opposite of timesing something by 4? And what's going to happen on the other side when I have 0 divided by 4? It's 0. So I'm going to end up with a to the 9 greater than or equal to 0. How do I get rid of an exponent of 9? I ninth root it. Well, what's going to happen on the other side when I take any kind of root of 0? So this is telling you that a has to be greater than or equal to 0. That's what the question is asking when it says, for which values of the variable is the radical defined?
Yeah, that does kind of make sense, like the whole not being able to square root negative roots, not being able to square root negative numbers thing, because I just remembered, so for, normally, if you want a square of something, you just times the number by itself, like 4 times 4.
But it has to be exactly by itself, right? Can't be negative of itself, has to be exactly.
Yeah,
Can I just pause you for a second? What about cube roots? Why, I don't know who said, was it Ethan? Why can you have negatives with a cube root? I didn't hear what he said. It's an odd number. So if you took a negative times a negative times a negative, what's that going to end up being? Negative. And a positive times a positive times a positive? Positive. So really what's going to happen with a question like this, it matters what the index is. If the index is even, the radicand has to be positive. If the index is odd, it doesn't matter. I'm going to repeat that for the wordy people. If the index is even, the radicand has to be positive.
Yeah, see, that's exactly what I was getting to. I mean, a negative times a negative ends up still being a positive. So yeah, with negatives you can't do that. The square rooting, cube rooting and stuff. Yeah.
And the second part of that, if the index is odd, it doesn't matter. Radicand can be positive, negative, doesn't matter. It can be anything you want it to be. At first, this question is going to bother you, and once you practice it enough, this question always becomes the same whether it's even or odd. Do not blow this question off in the homework and just not do it, because then you're not practicing. So it's like a really hard dance move or a hard piece of music. You can't just avoid it forever. This is going to come back unit after unit after unit is what values of the variables are defined. Because in science, we care when a variable is undefined because it throws out a whole science experiment. Right? If we're doing all this calculation, all this stuff, and suddenly we get negative square root, we're back to the drawing board. Okay. Next example. We're not going to do this radicand stuff. We're just going to do straight. Let's convert this to an entire radical. Caitlin? So if the radicand is even, or sorry, if the index is even, radicand must be positive. Oh, solving it for 0. Solving it for 0. Okay, so this one we're just back to entire radical. So this is our two-stepper. The method's on the last page. We're going to grab what's ever in front. We're going to throw it under the radicand, and we're going to, what's the other part of that step? Before we simplify, we throw it under, and we give it an exponent. Again, some right brains, it helps if you circle everything that's in front, because then your brain can see a little bit easier what's happening. If you don't need to circle, then don't circle. So keeping my radical symbol, keeping my AB that's already hanging out under there. All I'm going to do is take the whole coefficient, throw him under, and what exponent do I need to give him? A 2. Why a 2? Because it's a square root. Step 2 is our simplifying. Again, AB is just going to hang out up front, not going to worry about him yet. I need to square 4a squared b. So again, this is the exponent law, says we apply this to everything. So we need to go 4 squared, which is 16. I need to go a squared squared, which is a to the 4. And then I need to go b squared, which is equal to b squared. Now there's just a lot of stuff hanging around, so now I'm going to collect it. Coefficients go first, and then we collect the like terms. So 16 is going to go in front. If I have an a to the 1 and an a to a 4, and I'm multiplying them, I get a to the 5. And if I have a b to the 1 and a b squared, and I'm multiplying, I get b cubed. There's converting a radical to an entire radical. Ready to go backwards? Not so much. You can do it. Backwards is easier. So this is called simplifying radicals. And we're going to start with a question you did last semester, and then we're going to build upon it. So I put the method here. I don't know if this is the way JR explained it. It's the way I explain it. So if that works for you, great. If you have a different method, that's fine too. However you learned this last semester, that's fine by me. So convert 50 to its simplest form. How did you do this last semester? This silence scares me a little bit. Thank you, Ethan. Could you be a little more specific? Because everything I do has numbers in it. And I could whip out some grade 12 pre-cal and scare the pants off you right now.
Oh, God, no.
Okay, so you broke it into 25 and 2. That's what I'm asking? You're looking at me like I'm an alien? Does that look familiar?
Somewhat.
Okay. And then what can we do once we have two numbers under the, or as the radicand? We break them up, so we can say this is root of 25 times root of 2. And then we evaluate the one that's even, so we can evaluate this one as 5, and then we leave the other one. Does that look familiar? So my method I have here is a little bit different. If it works for you, great. If this works for you, great. That doesn't matter. We're doing the same thing, just look what we're doing it to now. So we're going to add some cube roots. We're going to add some variables. Exactly the same procedure. We're just mixing this up a little bit. Are you ready? What I'm going to do first is I'm going to break up 108. And I'm looking for perfect cube numbers this time, not perfect squares, because this is a 3. So I do prime factorization, which is not the method here. So I'm going to show you that. If you're like, what the? Don't worry about it. I'll show you another method in a second. What I do off to the side is I break up 108 into its prime factors. And you can't see that. And prime factors are numbers that can only be divided by 1 in itself. What's the smallest even prime factor? So I always start with 2 because my head can divide by 2 really easily. So it's 108 divided by 2, and my brain breaks that into 108. And then it breaks 100 into 2, which is 50, and 8 into 2, which is, and then it puts them back together, so this is 54. Well, this is still even, so what can I break this down into further? 2 and 27. This is not the only way to prime factor. I could have done that into other factors. I'm just showing you how my brain does it. Okay, you need to break 27 up, so 3 and 9. And then I can break up 9 into 3 and 3. Does that look familiar either from grade 9 or from last year? Or last semester, I should say. And then what I do is just collect it. So I've got 2 to the 2, because I have 2 of them. And I have 3 to the 3, because there's 3 of them. Are we okay there, what I did?
I think so.
Okay, so what I'm going to do is just put that back underneath. I'm just going to put my 3 to the 3, and then my 2 to the 2. And I'll tell you in a second why I put the 3 before the 2. And the negative just tagged along. I didn't worry about him. He was in front of the 108. Now he's in front of that. Not going to worry about him. Are you okay so far? What I'm going to do with my a to the 11, we know that means I have 11 a's. What I'm going to do is put them into groups of 3. So if I have 11, I can make one group of 3. Can I make a second group of 3?
Yes.
Can I make a third group of 3?
Yes.
Can I make a fourth group of 3?
No.
No. So what is the largest multiple of 3 that's in 11? It's 9. So I'm going to break it into a to the 9. And what's my leftover? What's my leftover? 2. Okay, so all I did was break those a's just like I broke up 108. Why did I choose groups of 3? Why didn't I break 11 into 5 and 6? Why didn't I break it into 7 and 2? Why did I choose to do groups of 3? Because it's a cube root out here. Is it somebody I want to talk to? Oh, we want to talk to her. Is she crying? Wait. Is she crying? Give her a hug if she's crying. What was that? As she was at the door, like, it's Marjorie. I'm like, well, told you they lied to me.
We can see their walls.
I would have let you in either way, though.
Thank you.
How are we doing so far? Again, it's the first time you're seeing it, so you're not supposed to be perfecting it at this moment. You're supposed to be just being able to follow.
I'm following okay so
Okay.
far.
All I'm going to do is exactly what I did here is I'm just going to break this into 2 radicals now. I'm going to have one radical that's a cube root, and I'm going to have another radical that's a cube root. I'm going to take the perfect cube, so I'm going to take the 3 to the 3 and the a to the 9, and I'm going to put them together, and I'm going to leave the crap that's left over by itself. I don't care where the negative goes. I'm just going to happen to tag it along with the 3, but it doesn't matter. So I'm going to have a 3 to the 3 in this one, and I'm going to have an a to the 9 here. What's left over? A 2 to the 2 and an a to the 2. And again, that negative could have followed in either radical. It doesn't matter where the negative goes as long as there's one in there somewhere. All I have done is split exactly up here because I can take the perfect square root of 25. I've split these guys because I can take their cube root perfectly. So what is the cube root of negative 3 to the 3? Well, what's going to happen is these are going to cancel. So if I'm taking a cube root and then an exponent, it's gone. What I'm left with is negative 3. If I take the cube root of a to the 9, so I'm taking a to the 9 and splitting it into 3 groups, how many a's are going to be in each group? So I have an a to the 3. What's going to follow it? Well, just like up here, my root 2 just tagged along. I call it the root of the crap is going to stay along. I don't care about the rest of the stuff because I can't cube root it perfectly. There's doing a mixed radical. It's exactly what you did last semester. We're just upping the ante a little bit. We're throwing in cube roots and we're throwing in variables. Process has not changed. If you have a different method from last semester that worked for you, use it. This is just how I do it. This is heavy for Friday afternoon. Okay, let's break the numbers down a little bit smaller this time. So not so big, not as many variables. Let's just do the cube root of 128x. Again, what I like to do is take 128 off to the side and break down the prime factors. If that's not your method, then you don't have to do that. If it's even, I like to start with 2 because my brain divides by 2 really, really nicely. My brain grabs 128, and 100 divided by 2 is 50, and 28 divided by 2 is 14, and then I smush them back together and we get 64. And if you need to write that out, then do it. Visual people tend to see things. I'm an air drawer, so I'm actually visualizing it in my head. And I know this is even, so I'm going to do 2 again. And it would be 2 times 32. Now my brain can see that this is 2 to the 5. If your brain doesn't see that, then you would just keep dividing by 2. You can stop wherever your brain needs to stop. In total, how many 2's do we have? 7. So I know this is 2 to the 7. That's really what you need to get down to, however you choose to do it. And then what your brain needs to do is put this into groups of 3. How many groups of 3 are in 7? 2. So I've got 2 to the 6, and my leftover is 2 to the 1. Why am I choosing to put it into groups of 3? Because this is a cube root. If your brain would rather write this as 2 to the 3 and 2 to the 3 and the leftover 2, that's fine. Some brains see it easier when it's 3's and 3's. It's whatever your brain sees easier. We're just grouping it by 3's because we're doing a cube root. Okay, so now I'm coming here, I'm keeping my cube root, I'm keeping my x, I'm just going to break these guys into 2 to the 6 times 2. Now we're going to split up the pieces just like we did before. So cube root of 2 to the 6, cube root of 2x, so the leftovers go together, the perfect cube is going to come out front. The cube root of 2 to the 6. 2 squared, so 6 divided by 3 gave us the exponent of 2. So if you need to write a little note where this came from, it's 6 divided by 3. And I'm just keeping everything that's left. I call it the crap in the back. And now I just need to finish by simplifying. We would never leave 2 to the 2. We would write it as its normal number. What's 2 to the 2? And the crap that's left. There's simplifying a radical that's a cube root and has a variable. For which values of the variable is the radical defined? What is the question asking you? What does that really want to know? What can x be? What are the good numbers? What are the bad numbers? What can we put in for x that's going to work? What can we put in if it's not? Well, what do you know if the index is odd? It means it can be any single number. It doesn't have to be just positive. Well, how do I mathematically say x can be any single number and it doesn't matter? How do I say that in a little shortened version of math notation? Yep, somebody's drawing it in the air. X. I know you wrote this about 100 times last semester. X can be any single number in the world. X can be negative, it can be positive, it can be a fraction, it can be a decimal. I'm ready to high five. Ooh, because that's a positive. How do I say X can be any number? X-E-R, there it is. Remember that from last semester? What do you mean he didn't show you that at all? Okay, well, let me just tell you. That's just notation. It's just misplacing English words for math. This is the Greek letter epsilon, so it's always like a C with a straight line. It's not a curvy E. It's not an English E. It's called epsilon. Now I can't spell it. Epsilon. There's an S in there somewhere. I think there's an S in there. It means in Latin, which translates into English, is an element of. And again, you don't need to know all this. It's just interesting where it comes from, and it helps some brains understand. Is an element of. And the capital R with the double bar at the back, that just means the real numbers. Is she crying?
No.
Oh, she's smiling. That's the, oh, and she has a note. I'm kind of excited. Marjorie, I can't believe you did that. No, it's
Honestly, when you asked when she was crying, you said, "No, a little too excited there."
because I was waiting for Alex to give her a hug, and then we'd all like, oh, and then didn't need one. So that's all this is saying. All it is saying in math notation is x is an element of the real numbers, and x is an element of the real numbers is a fancy way of saying x can be any single number in the world. Whew, let's back up. Why can x be any single number in the world? Because the index is odd. So we can cube root a positive, we can cube root a negative, we can cube root a decimal, we can do whatever we want with a cube root. Whew, how are we doing so far? Yeah, I'm a little tired too. It's heavy for a Friday.
Really tired.
Okay. Are you ready? Square root, double variable. We can do this. What do you want to do with 48? So we can either prime factor, or if you can see the perfect square right away, we can jump right to it. It's totally up to you. Okay. Yes, the other number would be 6. Neither of those are prime factors, so we got to split them. I think that's what I heard. Okay, some prime factors in there, but are we done? Okay, so let's just put all that together. So I have 2 to the 4 times 3. Oh, you can't see that. 2 to the 4 times 3. If your brain likes the actual number better, well, what is 2 times 2 times 2 times 2? It's 16 times 3. And that's the perfect square, and that's why we like it. So I'm going to take 48 and make it 16 times 3. What am I going to do with a to the 7? So I want to split it into groups of 2. Why groups of 2 when we were just doing groups of 3 in the last example? Because it's square root. So what's the largest number in 7 that's a group of 2? So I have a to the 6 and an a left over. What about b to the 6? I don't want to split that into anything. I want to leave it because it already is an even number. So I'm just leaving it. Okay, let's put the good stuff into one radical, the leftovers into the other. So 16 is a perfect square, a to the 6 is a perfect square, b to the 6 is a perfect square. What's left over that we can't use? 3 and a. And let's evaluate everything that's in that first radical. So the square root of 16, square root of a to the 6, a to the 3, square root of b to the 6, b to the 3. And again, if you want to make a note, the 3 is coming from 6 divided by 2. And then the stuff that's left just hangs around there. So the mixed radical is 4a cubed b cubed times the square root of 3a. Next one. Fraction. Yeah, you're going to find 81's a better number. Okay, well, it's a cube root. We're not going to panic. It's a fraction. We're going to use the same skills we have. What would I do if this was just 40? No, no, oh crap. No, no, fractions are our friend. If there were no fractions, we could never split pizza.
Admittedly, yes.
Okay, if this was just 40, so pretend the bottom isn't there. What would we do if this was just 40? We would prime factor. So let's just do that off to the side and not freak out about the 81. Let's just do our 40.
Okay, good idea.
No freaking out, just 40. 40 is a nice number. 2 times 20, I heard someone say. 2 times 10. 2 times 5. Done. Okay, group what we have.
And then just went right to 4 times 10.
Yep. So we have a 2 to the 3 times 5. And again, if some people like the actual number, so 8 times 5, that's okay. You can use 8 times 5, whatever your brain likes better. Okay, well, what if the number was just 81? So now let's pretend the 40 wasn't there. If this was just the cube root of 81, what would we do with 81? We would prime factor 81. Sorry, 27 and 3. Nine and 3. 3 and 3. So how many 3s do I have? But how do I want to group them? In 3. So I want to write this as 3 to the 3 times 3. Why am I not keeping it as 3 to the 4? Because I need to cube root it, so I need groups of 3. Again, if you would like the actual number, so 27 times 3, if your brain likes that better, then put that one, whatever you want. Okay, so I'm not letting this fraction freak me out. I just did the 40, so now I'm going to put in either 2 to the 3 times 5 or 8 to the 5, 8 times 5, whatever you prefer. And I'm putting the bottom in, either 3 to the 3 times 3 or 27 times 3, whichever your brain prefers. And I'm going to split this into 2 radicals, just like we've done every other question. I'm going to put the good stuff in the first one, so my 8, my 27. I'm going to leave the not so good stuff in the back, the 5 and the 3. And then we're going to evaluate just like we did before. So what is the cube root of 8? Well, you know over here, cube root of 8 has to be 2. What's the cube root of 27? Well, you know from here it has to be 3. What do I do with that second radical? I just write them behind. They're simplifying a radical fraction. So I have 2/3 times the cube root of 5/3. Did the process change because it was a fraction? No, we still did the exact same steps. We just did it for the top and bottom separately. How are we doing? One more little thing to go. That's it. I know it's Friday. I know. We can do this. We can do it. So last thing we need to be able to do is order radicals, just like you did ordering fractions and ordering decimals and ordering integers. Now we're ordering fractions. So radicals. Put the following set of radicals in ascending order. Highlight or circle ascending. Is that getting bigger or getting smaller? Bigger. Ascending is going up. What's the opposite? Descending, which is going down. So this we want from smallest to larger. Methods. Step 1, we're going to convert them all from all the mixed radicals to entire. And then we're going to compare them. Well, this is why we just practice the converting, because if we have them all like this, well, now we have to estimate. Well, is 2√3 bigger than, we don't know. Well, let's put them all into entire radicals. So how do we change an entire radical? We just practiced this a couple examples ago. We take the 2, we shove them under the root, and what do we give them? An exponent. Okay, so the first one, the 3 is still going to stay under there. I'm going to shove the 2 under there, and I'm going to give them the exponent of 2. I'll simplify them in a second. I'm just going to do the same step for the other 2 radicals. I'm going to keep the 5 for the second one. I'm going to shove the 4 under there, and I'm going to give them the exponent of 2. 3. Okay, well, I'm going to put them under a root. There just happens to be nothing else there, and I'm okay with that. So I'm going to shove 3 under the radical and give them the root or the square, the exponent of
1.
Well, if I gave this one a 2 and this one a 2, probably I'm going to give him a 2 as well. Okay, so if it's just a number, we're just doing the same process. There's just nothing else hanging out there. What do I do with root of 8? There's nothing up front.
Oh, crap, I missed it before for a fourth root.
Right brains.
So bad. Stupid right brain.
What do I do with 8? Yeah, so if I put a 1 in front and I shove a 1 underneath, what's going to happen? Yeah, because it's already an entire radical, so I don't have to do anything to 8. Again, if you didn't know that, you would put a 1 underneath, you would square 1, and 8 times 1 is itself, so it doesn't matter. Okay, let's do the step 2 for each of these, which is the simplifying. Exponent comes first, so 2 to the 2. 4, and then times 3. The second one, 4 to the 2. Times 5, and if you have to break 6 and 10, and then multiply those by 5 and smush them back together, do that. 80, 84, 80 confirmed, 80 confirmed. And then we get something like this, we're like, yeah, we had not a lot of thought here. What's 3 squared?
9.
And then, yeah, I don't even have to think about root of 8. Now do you see why we change them to entire radicals? Which one is the smallest? Square root of 8. The next smallest? Square root of 9, followed by square root of 12, followed by square root of 80. And then to finish off, we're just going to put them back in the same form the question gave us. So 8 was which of these? Itself. 9 was 3. Root 12 was 2 root 3. And root of 80 was 4 root 5. There's ordering radicals. Whew, thank you for that.